Hello, this is Team 5, REA Crew, and this is our solution to the evidence one. The challenge was to make a Puzzlebot navigate with no human input at all. The robot had to stay centered in a line, react to traffic lights and 7 types of traffic signs, and decide what to do at intersections. For example, turn left, turn right, or go straight. The robot is a Puzzlebot with a differential drive chassis. It's equipped with a Raspberry Pi Camera V2 for all vision tasks, a Jetson Nano for onboard AI processing, a hacker board reaching the computer with the motors and encoders, a Wi-Fi antenna, and a battery. The solution runs on 6 rows 2 nodes, each with a single responsibility. The line follower processes camera images and calculates how far the robot is from the center of the lane. The traffic light detector analyzes color to determine the current light state. The image compressor prepares frames for YOLO, resizing, converting to grayscale, and compressing before inference. The sign detector runs YOLO V8 to classify traffic lines in real time. The odometry node integrates encoded readings to estimate the robot's position and orientation, and the controller node is the brain, because it receives data from all other nodes and decides velocity commands through a finite state machine with 6 operating modes.
And for the software architecture, we have the camera and encoders. We have the node possible odometry that read the velocity of both encoders and publish in odom topic. And we have the camera that's published in video source raw. This image is used by traffic light detector that publish the traffic light state and used by the image compressor that compresses this the raw image in a GPG image compress. So in video source YOLO compress topic, this topic is used by traffic sign detector and publish the traffic sign state. And the line follower use the video source YOLO compress image to publish the line error and intersection detect. All these final topics are used by line follower controllers to publish the command of velocities to the motors of the puzzle. For the navigation logic, we use a pulse estimation using the odometry, and we detect the intersection using the bottom of the image. And we have our finished state machine with 6 modes. The first one is follow, that he follow the line with a PT controller. The next is the wait intersection, that here stops 1 second at a crossing. Then make turn or straight. The next state is turn. Here we have 3 phases. The first one is forward, then rotate, and then exit. The next one is straight. He advanced 0.45 meters. And the special, we have the signals round workers and give way. And finally, stop when the velocity is 0. And for test our system, we validate independently. First, we validate the line following. Secondly, we validate the traffic light detection, then the sync reconnection with YOLO. And finally, we made a full integration of all the nodes in our systems. And here we can see how the validation was successfully. We can know that the signals were identified and the puzzle bot follows the line.
For the experiments, we test the complete system with all the main models working together. The only thing we changed in each experiment was the order and type of traffic signs on the track. The results showed that the Puzzlebot could react correctly to different scenarios, including turns, caution zones, yield behavior, and full stops, just as you can see in the following videos.
Even though this is a small scale project, we connected to two SDGs with SDG 11 because we work on exactly the same problems a real autonomous vehicle would face, with design, perspective traffic lights, making decisions at intersections. It's the same problem, just smaller. And with SDG4, because we collaborated with Manchester Robotics on a webinar to bring these topics closer to younger students. On the ethics side, 4 points we find relevant for any system like this is who is responsible when it fails, bias in training data, transparency, which we have since everything in our system is interpretable, and privacy due to the constant use of a camera. We achieved the main goal. The robot navigates the full circuit autonomously. The ROS2 architecture worked well. YOLO V8 with transfer learning hit 0.918 F1 score on a small dataset, which was a pleasant surprise. The clearest limitation was HV-based traffic light detection, which struggles under changing lighting. In terms of learning, we understood in practice that integrating subsystems is harder than building them separately. Debugging in a real hardware, network latency, variable lining, encoder issues, that was our day-to-day. Connecting back to the ADGs, what we build is exactly the type of technology that scales towards safer and more efficient urban mobility. It's not a Tesla, but it solves the same fundamental problems.